We've talked about water and how important it is in acids and bases, and how it can also act as either an acid or a base. And so in the case, since that's the case, we can put two water molecules together and react them, and they will be in an acid-base reaction, where one of the water molecules is the acid and the other is the base. And then the acid is going to lose your hydrogen and become a hydroxide, and the other will be a base and form a conjugate acid of H3O+. And so we can write the equilibrium constant expression for that by saying that the constant K is equal to the hydronium ion times the hydroxide divided by H2O squared, because I have two of those. And these are the products over the reactants. Now the Kw then becomes hydronium times hydroxide, because if I multiply both sides by the water, that will cancel that out. And so this is the ion product constant for water. And experimentally what we have seen is that these are going to be constant. So if the H3O plus is equal to the OH minus constant at 25 degrees, the H3O plus concentration is equal to the hydroxide concentration, and they're both equal to 1 times 10 to the minus 7 molar at 25 degrees C. This was shown experimentally. So your Kw is equal to hydronium ion concentration times hydroxide concentration. So if they're the same, you multiply them together, and the Kw becomes 1 times 10 to the minus 14. So the Kw for all aqueous solutions at 25 degrees C is 1 times 10 to the minus 14. So that's why when we look at this, it has to be in water. And so what that allows us to do, since we know that the Kw is always 1 times 10 to the minus 14, then we can, if we know the hydronium ion concentration, we can find hydroxide and vice versa by just rearranging this formula to solve for the hydroxide, which is going to be the Kw, which is 1 times 10 to the minus 14, divided by what that concentration was. Also, if we know the hydroxide and we need to know the hydronium, since we know that the Kw is 1 times 10 to the minus 14, then we just divide by the hydroxide concentration and get the hydronium. So whichever one you know, you just divide the 1 times 10 to the minus 14 by that concentration, and that will give you the concentration of the other one, because they must remain at a constant of 1 times 10 to the minus 14. So the way you'd use that is in a problem, if you have the hydronium ion concentration in a cup of coffee is 1 times 10 to the minus 5 molar, then what is the hydroxide concentration? So since you know the hydronium, you're going to divide your Kw by the hydronium ion concentration, and you're going to get the concentration of the hydroxide. Make sure that you can put these numbers in your calculator, and when you hit enter you get this, because when you work these problems you've got to be able to do these correctly. Now just a little algebra reviewer here. If you have exponents and this is 1, okay, so it's 10 to the minus 14, 10 to the minus 5. If you're dividing, you add. So you subtract. So if you divide exponents, you're going to subtract them. So you've got a minus 14 minus a minus 5. Okay, that gives you a minus 9. If you multiply, then you add them together. Okay, so if you're multiplying two exponents, then you add them together to get the exponent. Notice that when you get this number, if you had 10 to the minus 5 and 10 to the minus 9, if you multiplied that together, you would add minus 5 plus minus 9, and you would get minus 14. The only thing on these that's difficult mathematically is making sure you keep the negative sign and use that correctly. So in dissociation of water, if you dissociate water in a neutral solution, your hydronium and your hydroxide are going to be equal concentrations. The hydronium will be 10 to the minus 7. The hydroxide will be 10 to the minus 7. If it's in an acidic solution, you're going to have more acid, so more hydronium than you do hydroxide. Okay, so you'll have higher than 10 to the minus 7 of your acid and less than 10 to the minus 7. If it's basic, you're going to have more hydroxide or less acid, whichever way you want to think about it. So you'd have less hydronium and greater hydroxide. So this leads us to the pH scale, because the pH is defined as the negative log. That's what P stands for when you see it in front of something. The negative log of the hydronium ion concentration, because pH is a measure of acidity, how acid is something. So the lower the pH is, the higher the concentration of hydronium ions. And that's because we're using these negative exponents. And so remember that 10 to the minus 7 is less than 10 to the minus 6. Now, why is that? Because 10 to the minus 7 would be 0.00000001. 10 to the minus 6 would be 0.000001. Okay, so this number and this number is 10 times bigger than 10 to the minus 7. So even though that exponent number is smaller, since it's negative, it represents a bigger number. So in acidic solution, your hydronium ion is going to be greater than 10 to the minus 7. Okay, so that's going to be a lower number. And your pH is going to be less than 7. Neutral solution, the pH is equal to 7. Basic solution, the pH is going to be greater than 7.